Hi, my name is Tansey. I'm a PhD engineer from the University of Texas at Austin, and I did my capstone on pitfalls in image recognition solutions that rock. So just a quick introduction. Image recognition is used in social media to automatically tag your friends. Many of you have probably seen this feature on Facebook. It's also used in autonomous vehicles or self-driving cars to detect other cars or pedestrians, etc. The key here is that errors can be very costly, embarrassing, or put human lives at risk. And so my goal in this project is to study how image classification systems make mistakes using a simple example. So the state of the art for image detection is convolutional neural networks, and they're pretty complicated. So my motivation in doing this project is that neural networks are typically perceived as a black box solution, and I wanted to kind of get inside that black box and figure out how they work. So in a convolutional neural net, the image is basically put through a series of convolutional layers which pick up on features like edges or circular things. And then those features are learned and they're fed into a classifier that's used to make predictions, whether something is a car, a truck, or a van, a cat or a dog, whatever. So I did my case study to tell the difference between rock, paper, and scissors. I built a small convolutional neural network using PyTorch, and I trained it on images of rock, paper, and scissors. And the results are pretty good, so let's have a look at some of those. Here you can see predictions for scissors with very high probability of certainty in the prediction, so 0.99, 1.0, 0.97, etc. Same thing for paper. Paper is pretty easy. It's pretty much just looking for something that's kind of lighter with maybe a little bit of texture. And rocks are a little more complicated, but as you see, we have high probabilities associated with these, and finally, a false positive. Okay, I thought you said neural nets were accurate. Well, the model has never seen Dwayne Johnson before, so it classifies images as whatever category they're already most similar to. And in this case, Dwayne Johnson is more similar to rocks than to paper or scissors from the perspective of the neural net. You can see this if you look at the first convolutional layer that we feed things through. This is sort of like each node in that layer is activated by either rock or scissors. And you can see that rocks are lighting up certain nodes, and that Dwayne Johnson also lights up those same nodes. You know, if I flip back and forth, it's the same layers that are nodes that are activated. So, obvious solution to this is to train with the rock. Dwayne Johnson there gives us an inspirational quote that we need to train our neural networks correctly. So I simply added 500 images of Dwayne Johnson to the training set and problem solved. You can see the confusion matrix where we have the true label on the y-axis and the predicted label on the x-axis. Again, most papers predicted as paper, most rocks predicted as rock. Most images of Dwayne Johnson, however, predicted as rocks, as I showed you before. But after you train the neural net on images of Dwayne Johnson in addition to the other classes, we get this nice diagonal activation where most things are classified correctly. And a little funny here, you can see most of the rocks that are classified incorrectly are actually classified as Dwayne Johnson. So rocks look like Dwayne Johnson looks like rocks. Good to know. Unfortunately, this strategy requires the foresight to guess what kinds of weird images our net might encounter. So can we do anything preemptive to solve this problem? If you look at a histogram of the confidence of behind predictions, on the x-axis is 0 to 1. You can see blue is the training classes, the base training classes, rock, paper, and scissors. They have very high confidence of prediction associated with them because the net was trained on them, the layers are kind of fit to them, so they activate things very consistently. Whereas Dwayne Johnson does not activate the same layers with the same consistency, so he's shown in red, and you can see a lot of the probabilities associated with them are around 0.4, 0.5. So what if we cut everything off here and set everything to the left, we're just going to throw that out and reject those classifications? Or what if we set the confidence threshold even higher? What would happen? Well, you would get a chart that looks like this, where the false positive rate for Dwayne Johnson is in blue, and that decreases as you require an increase in confidence level. What happens to the base classes if we require more confidence? Well, our precision in green is going to go up, but our recall is going to go down. So in conclusion, the basic problem that we're studying is that image recognition is trying to generalize from a training set. Mistakes happen when real life is more complicated than the set that you trained on, So solution 1 is to just get a better training set, and solution 2 is to recognize that the net kind of knows when it's confused and to let it tell you. This is my contact information. You can see my LinkedIn and GitHub profile. There's a notebook on GitHub that goes into way more detail on this project. Thank you very much.